Hello, I'm Donna Amaral Phillips from the University of Kentucky, and I'd like to welcome you to today's webinar sponsored by DAIReXNET and the National Association of County Agricultural Agents. Today, Pete Hansen will talk to us about cooling strategies during heat stress. Pete is a distinguished professor and an L.E. Red Largen Professor of Animal Science in the Department of Animal Science at the University of Florida. His research interests center around the development of methods to improve fertility. He joined the faculty at the University of Florida in 1984. His formal education was at the University of Illinois and University of Wisconsin. He is the past president of the American Society for Reproductive Immunology, and he's currently vice president of the International Embryo Transfer Society. He is actually the PI on the grant that came through NIFA that actually looks at the effects of heat stress on reproduction. And what he's going to talk about today is some of the cooling strategies that are needed to reduce heat stress. With that, Pete.
Thank you, Donna. I think as everybody who's listening knows, heat stress is a major problem affecting the productivity of dairy cattle. It causes about a 20 to 25% reduction in milk yield, has severe effects on fertility, and it's not only a major problem, it's a growing problem. Cows that produce more milk are more sensitive to the effects of heat stress than cows that produce less milk. So as we continue to improve milk yield per cow genetically, nutritionally, or through other management strategies, we're also continuing to make cows that are more and more susceptible to heat stress. So independent of any effect of global warming, we can anticipate that the cow of tomorrow will be more sensitive to heat stress than the cow today. Central to reducing the effects of heat stress on reproduction and on milk yield are strategies to cool cows during heat stress, to alter the environment that cows are in so that the magnitude of heat stress is reduced. So today I'm going to address this question of cooling strategies during heat stress, and there's really 4 take-home messages that I want to leave you with. So I'm just going to go through these one at a time. And the first take-home message is one that's probably obvious to you, but I want to take advantage of this message to teach a little bit of environmental physiology. And that take-home message is that when air temperature is high, that is when heat stress is a problem, the best method to reduce the magnitude of heat stress is to reduce the magnitude of solar radiation striking the cow, in other words, provide shade, and then secondly, to increase evaporative heat loss in conjunction with fans. The dairy cow can be considered in many ways as a furnace. Just like a furnace, she takes fuel sources, which in the case of the dairy cow is feed, and burns that fuel to produce heat. The dairy cow uses that heat to power all of the reactions in the body that are necessary for the animal to remain alive and to produce milk. So as cows produce more milk, they obviously need to burn more fuel, burn more energy to power the synthesis of milk, and as a result, the heat production of the cow increases. In order for the cow to be able to regulate her body temperature, to have homeothermy, as we say it, a normal body temperature of about 101.3 degrees Fahrenheit, she needs to match all of the heat that she produces as a result of metabolism, plus any heat that she might gain from the environment. This is usually solar radiation, with the heat that she loses to the environment. So in order for homeothermy then, the total amount of heat gained by the animal, either from production or from the environment, has to be equal to the heat loss to the environment. There are 4 modes of heat exchange, and it's important to consider these when designing systems to cool cows. The first mode of heat exchange is radiation, the transmittal of heat by ultraviolet radiation. or infrared radiation. So the major type of radiation that cows gain from the environment is sunlight. But it's important to remember that any object that has a temperature greater than absolute zero is producing radiation. So cows are gaining heat from the hot concrete, from the hot ground, from the hot roof, and they're also losing their own body heat as a result of radiation. The second source of heat exchange is conduction, and this just refers to the transfer of heat when one substance at a high temperature contacts another substance at a lower temperature. So typical types of conductive heat exchange are heat loss to the air that's not moving around the cow, heat exchange between the cow and the ground, like the freestall, for example, and also heat exchange with surface water. One very important point about conductive heat exchange is that the amount of heat transferred by conduction through water is 22 times faster than the amount of heat transmitted through air. So that when a cow is wet, when the air surrounding the cow is replaced by water, the cow loses heat 22 times faster than it would if it was surrounded by air. The third mode of heat loss is convection. Convection is basically the exact same process as conduction, except that two substances are moving past each other, which increases the rate of heat loss. So when we talk about convection in dairy cows, we're usually talking about heat loss that's facilitated by wind. The last mode of heat loss is evaporative heat loss. It takes a lot to evaporate a gram of water. So when water is converted from the liquid stage, the solid to the gaseous stage, it takes about 500 times as much heat as it does to raise the temperature of a gram of water by 1 degree Fahrenheit. So let's just look at these four mechanisms of heat exchange again: radiation, conduction, convection, and evaporation. These first three mechanisms of heat loss all depend on the magnitude in the difference in body temperature and environmental temperature. So as environmental temperature goes up, the rate of heat loss by radiation, conduction, and convection goes down. In other words, if it's 70 degrees outside and the body temperature of the cow is 101 degrees Fahrenheit, a lot of heat is lost by conduction and convection. But when the air temperature is 95 degrees Fahrenheit and body temperature is 101, there's not much heat lost by conduction and convection. Evaporative heat, in contrast, doesn't really depend upon air temperature. Rather, the rate of heat loss depends upon the humidity of the air. The more humid the air, the lower the rate of heat loss, the evaporation. So, let's just look at some examples here. It's easier for cattle to regulate body temperature when they're not producing a lot of heat. In other words, a non-lactating cow has an easier time regulating its body temperature than a lactating cow. It's easier for cows to regulate their body temperature when air temperature is lower than body temperature, or when solar radiation is not high, or when the cow can lose heat to the night sky. In other words, when it's housed outside so that it has the opportunity to lose its heat to the relatively cold sky as compared to the relatively warm roof or clouds. And it's also easier for cattle to regulate body temperature when humidity is not high. So let's consider a cow that's exposed to a moderate degree of heat stress but nonetheless lives in an environment in which it's able to regulate its body temperature successfully. So the example we have here is a cow with the air exposed to an air temperature of 85 degrees Fahrenheit, relative humidity of 50%, and she's under shade so that she's not gaining a lot of radiation from the sun. This cow is quite capable of regulating her body temperature. Because air temperature is 85 degrees Fahrenheit, she's able to lose heat by convection, lose heat by conduction. Because the relative humidity is 50%, she's also very effective at losing heat by sweating. By sweating, she's evaporating water to the environment and losing some of her body heat. And she's also capable of losing heat by respiration. When cows take air into their lungs, they humidify that air, and the heat required to humidify the air comes from the body temperature of the cow. And again, because there's not a lot of solar radiation, cows are losing heat by radiation to the environment. So this is a cow whose heat production matches its heat loss, and it's able to regulate its body temperature. Compare this cow with a cow in a much more severe heat stress environment. The air temperature is 94 degrees Fahrenheit, so the ability for conduction and convection to occur is greatly reduced. The humidity is 90%, so very little heat can be lost by this cow by sweating or by panting. And the cow is not under shade, so she's gaining a lot of solar radiation from the sun. As a result, she can't lose all of the heat that she's producing to produce milk to the environment, so her body temperature rises. And in this example, I said her body temperature was 102.4 degrees Fahrenheit. So if you remember way back when, my first point was the best way to cool this cow is to provide shade. So when we provide shade, we block the transmission of solar radiation to the cow and reduce radiant heat load. And the second thing we can do is provide evaporative cooling in the form of either sprinklers or foggers. By applying evaporative cooling, we increase evaporative heat loss as the water striking the cow gets evaporated. And we also increase conduction because as the surface of the cow is wet, she can lose more heat via conduction to the water, and heat loss by convection. And by applying fans in conjunction with soakers or sprinklers or foggers, we can increase the rate of heat loss by convection and also prevent the buildup in humidity that tends to occur when animals are sprinkled or fogged, so as to maintain this gradient or a low humidity so as to increase heat loss via evaporation. So as a result of these changes then, we can change the thermal balance of the cow. Maybe this cow is still hyperthermic because it's at a very high air temperature, but the hyperthermia is much less than it would be otherwise because heat gain from the sun is reduced, and we're helping the cow lose heat via evaporation, conduction, and convection. So keep in mind, not all shade is equal. It's important to give adequate amounts of shade that block solar radiation. Not all shade cloth, for example, or other shade structures does an effective job in preventing solar radiation from striking the surface of the cow. And it's also important to give enough square footage of shade, probably about 50 square feet per cow, so as to prevent crowding that would otherwise reduce the ability of the cow to regulate her body temperature. So compare this freestall barn from Mexico, where cows are given a very generous shade structure to this facility here. This is located at our research dairy at the University of Florida. This is an area for dry cows or cull cows, but you can see that this shade cloth is not doing a very good job at reducing the incoming solar radiation that strikes the cow. And also, cows tend to be crowded together because there's not much shade available. And when they're crowded together, their ability to lose heat to the air becomes reduced, because rather than being in contact with the cooler air, they tend to spend more of their time in contact with each other, so that conduction and convection is reduced. Okay, my second take-home message relates to the nature of evaporative cooling. There's many different strategies for cooling cows via evaporation. The availability of water and the housing system, whether cows are on dry lot or in freestall, probably has a major effect on the choice of evaporative cooling system. But I just want you to consider a few things about the nature of evaporative cooling. First of all, there's very little data as to whether sprinklers or foggers work best for cooling cows. If I had to guess, and I'll give you the reason why, probably sprinklers work best, especially when humidity is high. Tunnel ventilation is one method that's been used for evaporative cooling so as to combine convective heat loss using fans with evaporative heat loss. But as I'll show you in a minute, tunnel ventilation doesn't always necessarily work better than freestall barns for cooling cows. And then the last thing I just want to mention is that the cross ventilation type barn, which is really an improved design of the tunnel ventilation barn, may be very effective at cooling cows. There's very little data on that, but it also is associated with high investment costs. So a sprinkler system or a soaker system, like is shown in this slide, is really designed to wet the cow, to put enough water on the back of the cow to penetrate into the fur, or into the hair, I should say, and allow heat loss both by conduction, convection, and evaporative heat loss. In contrast, a fogger system is not really designed primarily to wet the surface of the cow. Rather, the purpose of the fogger system is to increase the evaporation of water into the air surrounding the cow. And when that water is evaporated into the air, the heat for evaporation comes from the air itself. So air temperature gets cooled, and that increases conduction and convective heat loss from the cow to the air. So really, a fogger system is like a primitive air conditioning system where evaporation is used primarily to cool the temperature of the air. So this kind of system is particularly poor when the humidity of the air is very high to begin with, since the air conditioning effect of the fogger becomes reduced. This is a primitive example of a tunnel ventilation barn. This is a freestall barn that's been retrofit to turn it into a tunnel ventilation barn. In tunnel ventilation barns, there's a bank of fans on one side of the barn, and air is driven through the barn by the action of these fans. And this wind tunnel effect is combined with evaporative cooling, oftentimes with foggers, although sometimes with sprinklers. So the tunnel ventilation barn, in principle, is an effective means of cooling cows, but in a lot of cases, its effectiveness is reduced by the fact that airflow past where the cows are actually located in the barn is oftentimes reduced. So if air is being pushed through this barn, where is it going to flow? It's not going to go through the cows because the cows are blocking airflow. Rather, the air is going to tend to move through the center of the barn, through the alleyway in the middle of the barn, where the cows are not located. So a lot of the convective cooling that occurs in a tunnel barn is oftentimes lost because it's going through the center of the barn. Also, vehicles are usually being driven back and forth in the barn to feed cows, for example, and that reduces the wind tunnel effect when feeding is taking place. Just recently, we looked at differences in body temperature of cows during the summer in various freestall barns in Florida as compared to two tunnel ventilation barns. So you can see the two tunnel ventilation barns were among the best barns for minimizing the increase in body temperature in the afternoon, but there were some freestall barns that were just as effective as the tunnel ventilation barn. I'll skip that slide for purposes of time since I already talked about this. So the cross ventilation barn offers the advantages of the tunnel ventilation barn, plus it reduces the problem of airflow. Because in the cross ventilation barn, rather than the fans being located on one of the longer ends of the barn, the fans are located on the side of the barn. So that in this system, air is being pushed across the side of the barn. And often, so the fans are located over here, and oftentimes the opposite side of the barn from the fans has an evaporative cooling pad where water runs through this cardboard structure, gets evaporated into the airstream, and provides a cooling effect. So here shows the outside of a cross ventilation barn, this one located in South Dakota, just illustrating this bank of fans on the side of the barn. There's very little data as to the relative effectiveness of the cross ventilation barn as compared to some other types of barns for cooling cows, but my guess is that it's a very effective method if designed properly, but also a very expensive alternative. The third take-home message relates to which animals should be cooled. Obviously, it's the lactating dairy cow that is most sensitive to the effects of heat stress because it's producing all of the heat of lactation that it has to lose to the surrounding environment. However, that does not mean that other animals on the farm are resistant to the effects of heat stress. And so I'm going to show you some data just to point out to you, don't forget cooling dry cows, don't forget cooling calves and growing heifers as well. Here's some data from the University of Florida from Jeff Dahl that illustrates the importance of cooling cows during the dry period and subsequent milk yield. The dry period is obviously a very important time in the life of the cow. It's when the mammary gland is going through the final stages, preparing for the next lactation. And Dr. Dahl and others before him have shown that if cows are heat stressed during this period, it has a long-term effect on subsequent milk yield. So what he did in this experiment was beginning 46 days before expected calving, cows were either maintained in a freestall barn without fans or sprinklers, that's the non-cool group, or they were placed in a similar type of barn where they were cooled by receiving sprinklers and fans. And you can see that the milk yield is much higher, on average 16.5 pounds per day higher, for cows that were cooled during the dry period as compared to cows that were not. So after calving, all the cows were cooled. All this difference represents pre-calving cooling. cooling for a relatively short period has a long-term impact on milk yield. We think about heat stress with the idea that it's the lactating cow that's so susceptible to heat stress. And that's true. Look at these data from the University of Wisconsin, which shows the relationship between air temperature and rectal temperature. So in lactating cows, as air temperature increases, body temperature increases. We usually think of infertility occurring at about 102.2 degrees Fahrenheit. And you can see these cows in Wisconsin are getting that hot at an air temperature of less than 24 degrees centigrade, so less than 75 degrees Fahrenheit. These cows are experiencing hyperthermia. Doesn't take a lot of heat stress to get a cow hyperthermic. Whereas in non-lactating heifers, it doesn't matter how hot it is, they're not becoming hyperthermic. They're not producing all the heat associated with lactation. However, even though non-lactating animals are more resistant to heat stress than lactating animals, that doesn't mean that they cannot experience elevated body temperature during heat stress. These are some data on vaginal temperatures in non-lactating cows. There's two cows shown here. One cow that's kept in a freestall barn with foggers and fans, and one cow that's placed out in a lot with shade cloth as the only way to cool the cow. And you can see that these cows maintained in the freestall barn with foggers and fans regulate their body temperature very nicely, but these cows that are placed out in a lot with just shade cloth, they become hyperthermic, so hyperthermic fertility would be affected relatively early in the morning. So they spend most of the day at body temperatures much higher than those necessary to prevent conception. So if you want to get heifers bred during periods of heat stress, it's important to keep them in an environment where they do not become hyperthermic. So some cooling is necessary. Even baby calves need to be cooled. We've measured body temperatures on baby calves in hutches in the summer that had temperatures as high as 106 degrees Fahrenheit. So who knows what the long-term effect of that severe of a increase in body temperature is on the long-term growth of that calf. But even a relatively minor heat stress can compromise growth of the calf before weaning or after weaning. These are some data from the Slovak Republic where it doesn't get all that hot. But if you look at the growth rate pre-weaning for calves born during the hottest time of the year, June 12th through September 14th, you can see that their growth rates are lower, 0.1 pounds per day lower, than for calves born either earlier or later in the year. So providing to growing calves, to dry cows, to heifers, as well as to lactating cows. All right, the last take-home message is to measure how good of a job you're doing cooling cows. And I would suggest measure body temperatures of some sentinel cows so you can decide for yourself how good of a job your system is doing at preventing hyperthermia. Also, you can measure differences in performance, in lactational performance or reproduction between the summer and the winter to determine how good of a job you're doing at cooling cows. So we usually measure heat stress in cows by looking at the temperature humidity index, which is just a mathematical combination of dry bulb temperature or air temperature and relative humidity. And these kind of charts, like are produced at the University of Arizona, give you a rough ballpark as to whether or not cows are in environments where they're heat stressed or where they're not heat stressed. But these charts by themselves do not give enough information as to how heat stressed cows are on your farm. I'm going to skip these. What's more important is whether or not cows can keep their body temperatures low enough to prevent effects on milk yield or conception rate. And kind of the critical number to think about is 102.2 degrees Fahrenheit, 39 degrees centigrade. Milk yields start to decline, conception rates start to decline in cows that have rectal temperatures above this. Oftentimes, vaginal temperatures are measured instead of rectal temperature. Depending on the method of measurement, they're either the same as rectal temperature or a little bit higher. So it's very easy to measure body temperature in cows during the day. It can be done on the farm with very little sophisticated equipment. We use this iButton, which is a little thermal-sensitive computer chip that records temperatures at various intervals as often as every minute. We probably measure it every 15 minutes. So you can take an iButton. It costs about $20, which can be used over and over again in cows, where you can download the data to a laptop computer very easily. Take an iButton, put it in an empty seeder, put a little bit of aquarium sealant in there to fix it in place, pop this in the vagina, and you can measure body temperature over a 24-hour period of time and see when cows are becoming heat stressed, when during their daily routine. And this information can be used to help you identify times of day or physical location where cows are not receiving adequate cooling. If you're really interested in these iButtons, this is the catalog number of the iButton we use. There's all sorts of these sold, but this is the one that we use, and this is the product information. So let me give you an example how this information can be used. These are some body temperature data, vaginal temperature, for lactating Holsteins on a grazing dairy in Florida during the summer. So shown here is the daily rhythm in body temperature for these cows during the summer. So what's the first thing that we can learn? Even at night, these cows are hyperthermic. Even at night, they have a body temperature that would cause infertility. So they're likely not to be very fertile. They're likely to be experiencing effects of heat stress. In the morning, they get milked, and as part of the milking process, they're cooled down in the holding area. And you can see that's a very effective way for cooling those cows. Their body temperature drops to less than 101 degrees centigrade while they're in the parlor. And then when they come out of the parlor, their body temperature rises again very rapidly. But you notice that during the afternoon when they're grazing, their body temperatures aren't that much higher than they are at night. And that's probably because this dairyman grazes these cows with the irrigation pivot that's been modified to provide evaporative cooling to the cows. So he's able to reduce some of the effects of the solar radiation associated with grazing by giving cows access to this irrigation pivot. Then in the afternoon, cows go in the parlor again, body temperature drops, but not as much, probably because air temperature's higher now, and then body temperatures go up again. So what would I learn from this if I was a dairyman? First of all, I'd learn that my irrigation pivot's probably worthwhile because I'm preventing some of the increase in body temperature that I could expect by having these cows grazing during the hottest time of the day. Secondly, I'd realize that I might be able to get some additional cooling if I could develop a mechanism to cool cows at night, either by placing some kind of cooling system where the cows loaf, or by providing cooling stations like has been tested in California, where cows can walk up, let's say, to an evaporative cooling device and cool themselves. This is this dairy. You can see how this irrigation pivot's been modified to provide a lot of soaking ability here, and the cows graze during the day right underneath the pivot. So maybe that affects feed intake a little bit, I'm not sure, but it certainly affects body temperature in a positive way. Okay, the last point I want to make. One of the things that we're trying to do in this USDA grant, Todd Bilby at Texas A&M is doing, is to develop summer to winter ratios for milk yield and conception rate in U.S. dairy herds. This is an idea that was originally developed in Israel. So in Israel, the Israeli herd book calculates for each farm the summer-winter ratio in fertility and the summer-winter ratio in lactation. And by comparing that ratio to your neighbors under similar conditions as you are, you can get an idea whether you're doing a good job cooling cows or a bad job cooling cows. So this data in this slide just shows the average summer to winter ratio for cows in different kinds of herds. So let's just look at this for a second. These data have been divided up into high production herds and low production herds. Some herds receive intensive cooling, and in Israel this means bringing cows to cooling stations where they're sprayed and fanned 10 times a day, whereas the moderate cooling herd only gets cooled when they're in the milking parlor, when they're in the holding pen. So you can see that in the winter, the fertility in these two types of farms is identical. And in the summer, fertility drops in both types of herds. But it drops more in the moderate cooling group than it does in the intensive cooling group. So it's 12% in the moderate cooling group, 19% in the intensive cooling group. So the summer-winter ratio is higher for the intensively cooled cows than for the moderately cooled cows, demonstrating the effectiveness of applying this extra cooling for improving fertility in these dairy herds. You can calculate summer-winter ratios yourself by using your own herd data. It won't be completely accurate because it won't take into consideration seasonal variation in days in milk, parity, etc. But eventually, Todd Bilby and his colleagues are going to develop a system for calculating these ratios on a national scale so that we can get some good estimates on individual farm basis for how well cows are being cooled. So to summarize, cool cows by providing good shade and a combination of evaporative cooling and fans. In general, the more water, the better. I know it's not always available, and problems associated with wet bedding, etc. can be a problem, but the more water you add, the more cows get cooled. Tunnel ventilation may not always be better than freestall barns or other systems, and I think cross ventilation is a housing system that may have some benefits. Don't just cool lactating cows, cool heifers, cool dry cows as well. There's economic benefits to doing so. And then if you really want to know whether or not you're doing a good job cooling cows, measure things. Measure cow body temperatures and measure the summer to winter ratio in fertility or in milk yield. Again, this talk and all the research behind it and the other 3 talks that have been put on webinars has been sponsored by a grant from the USDA AFRI competitive grant process. We do want to hear feedback as to how useful these talks are and what other issues that we need to be focusing on with respect to heat stress. So I'll be glad to take any questions now, and you can also email me at hansen@animal.ufl.edu. Thank you.
Thank you very much, Pete. So I'll go ahead and ask you a question, Pete, if you don't mind.
Good.
One of the things that's always very important, I think, is when do you start putting the fans and the sprinklers on? You had a chart in there that was Collier's chart looking at heat stress, and obviously it depends on humidity. But I think it's, a lot of times producers I work with, they wait too long to turn the fans on and the sprinkler systems on. So what would be your recommendation there as far as that's concerned?
Well, a ballpark figure, which is just that, is that high-producing cows start to become hyperthermic at air temperatures of 75 degrees Fahrenheit. Now, in a place like Florida, where cows become adapted to heat stress, they can probably cope with a little bit higher air temperature without becoming hyperthermic, maybe as high as 80 degrees Fahrenheit. But the ballpark figure I would have is somewhere between 75, 80 degrees Fahrenheit. Efforts ought to be made to cooling cows. And again, it's really easy to take a rectal temperature on a few cows in the afternoon and actually measure body temperature and get an indication whether or not the environment's at a point where animals are no longer able to regulate their body temperature.
So really looking at the cows themselves and in the system they're in, how well they can cope with the stresses that they're put upon is very important, is what I'm hearing you say.
Yeah, and those PHI indices that Arizona has developed are very useful, but they don't really consider the particular conditions in the environment that the cows are living in. How good of a job they are doing at preventing the solar radiation, et cetera, et cetera. So, I think you really need to measure the cows themselves to get a good idea.
Mm-hmm. We have a couple questions in the chat box, and we'll go ahead and take those. The first one, Paula asked about, you had a slide that showed conception rates for high and low production, and she was wondering if you could talk a little bit about what kind of yield was on that high and low production.
Yeah. Hello, Paula. I don't really know. Those high-producing herds in Israel are producing milk at about a U.S. level, or maybe even a little higher. So probably, in the high 20,000 pounds of milk. I don't really know about the low-producing herds, how low that is. It's probably pretty variable.
Mike Hutchins has the next question, a little bit different twist to it, but in your experience when you've worked with those herds in Florida that have used those irrigation systems, have you seen them be able to apply some fly control products coming through with the water in those systems?
That's a good question, and I have absolutely no knowledge about that. That's a really interesting idea, but I've never seen that done, and so I really couldn't comment as to how effective it would be.
I'm going to put you on the spot a little bit. Obviously, you talked a lot about the importance of preventing heat stress in lactating cows, dry cows, calves. Do you want to look at priorities? If you could only do one or two groups, what would you do? And where would you put your bang for your buck first?
Well, obviously lactating cow, especially lactating cow and early lactation before lactation peaks would be the number one priority.
And getting her bred.
Before she's bred, right.
And to get her bred, probably.
Exactly. And, one of the problems we have is that you can't just cool cows around the time you're breeding them, because the egg that's going to have to be fertilized can be affected by heat stress at least 30 days before estrus. So you can't just cool cows on the day of breeding or a few days before breeding and expect to overcome the effects of heat stress. So as a practical matter, if you want to have good first service conception rates during heat stress, you have to cool cows from the time right after freshening until first insemination. And unfortunately, in most systems in the United States, even if cows are receiving pretty good cooling, we're still not preventing that summer depression and fertility. And that's why I think some of the things that Todd Bilby was talking about in his webinar in terms of embryo transfer, really about the only way to get cows pregnant in the summer.
Okay.
The last animal I would cool, I would try to cool everything, but, cows that produce more heat are more sensitive to heat stress. So non-lactating animals, heifers, can probably regulate their body temperatures better in heat stress than non-lactating animals. And baby calves, who I do believe are oftentimes abused when it comes to preventing effects of heat stress, but still they are more resistant because they're not producing as much heat, and because they're so small, their surface area per unit body weight is really high. So they do a better job at regulating their body temperature.
I think I remember seeing some data out of Missouri that looked at immune function on calves that were heat stressed. It was reduced. So there's another aspect, not just growth, immunity.
Right, exactly.
Couple more questions. Are there any tools out there that are available to calculate heat stress reduction under different cooling type systems?
I wish there were, but they're not. And most of the systems that are being sold specifically as ways of cooling cows haven't really been compared to other systems that are being sold to cool cows. So it's a little bit difficult for somebody like me to recommend, let's say, Corral Cool versus some other system, because there's just not a lot of data out there to determine their effectiveness. It probably depends to some extent how they're installed relative to other cooling systems that are also put into place. So it's a difficult problem to address.
As far as cooling calves, do you want to comment about what you've seen as far as some good strategies for cooling calves?
I think the easiest thing to do is to prevent solar radiation, and the calf hutch doesn't really do it because depending upon the roof that is making up the calf hutch, it's very close to the calf. So as it heats up, it's going to heat up the air inside the hutch, and a lot of that radiation is going to be, or a lot of that heat is going to be transmitted to the calf from the air. And then as the roof heats up, because it doesn't have much opportunity to get cooled by the wind in many cases, it's going to start to produce radiation itself that'll be delivered to the calf. At the University of Florida, we have all the calf hutches under a big pole barn, so that the whole calf rearing area is receiving shade, and that seems to work pretty well. So that would be my answer, I guess.
I've seen in other parts of the country where they've taken hutches and in the summertime placed them under shade trees.
Yeah, that would be
tree line, fence row type deal, obviously rotating the hutches and stuff, but putting them under the shade trees or shade cloth. Seen shade cloth also used. Up high, though. There.
I think it's a good idea.
Pete, we really appreciate your time and the time of all the people on this grant to bring these webinars to DAIReXNET. Thank you very much.